Hi everyone, welcome to another video of this channel. So today I want to talk about a very interesting problem from the 2023 MIT PRIMES entrance problem set. Hopefully you will enjoy the solution as it is very interesting. So we have this function f from the real numbers to the real numbers, and basically the integral from y to y plus 1 of f of x dx is some linear function of y, and so is the integral from y to y plus root 2 of f of x dx. Given these conditions, we must prove that f is linear. All right, so first of all, when we have an integral and an easily differentiable function in the same equation, one nice thing that we can do is take the derivative of both sides. So that's what we're going to do. So we are going to do that for the first equation, and we are going to do that for the second equation as well. So now we have these two equations, which relate certain values of f to arbitrary real constants. The thing is, we don't know that much about these constants, so it would be nice to get rid of them. One nice way to get rid of them is to differentiate this again. And after we do this, we get that f prime of y is equal to f prime of y plus 1, which is equal to f prime of y plus root 2. So now we have this large equation which relates certain values of f prime, and we have to keep in mind what the problem wants us to do, right? We have to prove that f is linear. And really, the only way for f to be linear is for f prime to be a constant. So our goal is to show that f prime of y is a constant function. And usually, when we want to prove some fact about a function, we start with some of its properties. Here, from this equation right here, we see that f prime of y is actually a periodic function. It has two periods, 1 and root 2. And because it is periodic with these two periods, it is also periodic with every possible linear combination of these two periods. So we know that f prime will be periodic with every single period of this type right here. And speaking of periods, one nice property of constant functions is that they are periodic with every single real period. No matter what period you think of, a constant function is going to be periodic with it. Right? So let's say that we show that f prime of y is periodic with every single real period. Then f prime of 0 will be equal to f prime of y for every single real number y, and therefore, since f prime of 0 is a constant, f prime of y will be a constant function. So we can actually prove that f prime of y is a constant by showing that it is periodic with every single real period. But how are we going to do that? Isn't it only periodic with these periods right here? But wait, what if every single real number can be expressed in the form a plus b root 2? Then f prime of y will be periodic with every single real period and will therefore be a constant function. So our new goal is to show that this right here can represent any real number r. And maybe intuitively, after you play with some of the linear combinations a bit, it does seem like there's a lot of numbers that can be represented in this linear combination of 1 and root 2 form. But how do we prove this? One of the things that you might notice if you experiment a bit with these linear combinations is that you can get pretty close to 0. And this is actually a necessary condition for this goal right here to be true. A plus b root 2 must be able to represent any real number close to 0. And the reason why this is necessary for a plus b root 2 to be able to represent any real number is because let's suppose you've already expressed a number in this form, right? Let's suppose you already have the number 1 plus root 2. Well, you can add an infinitely small number to 1 plus root 2. Then you can add this infinitely small number again to get 1 plus root 2 plus 2 times this infinitely small number. And if we continue going in this fashion, we can densely cover the entire real number line with numbers of this form right here. So if we can prove that a plus b root 2 can represent any number as close to 0 as we want, we will prove that it can also represent any real number in general. So one of the ways to get started with this is to show that a plus b root 2 has no positive lower bound, right? The positive values of a plus b root 2 will always keep approaching 0 so that we can get these infinitely small numbers to be represented. So now the only thing that we really need to demonstrate is that the absolute value of a plus b root 2 does not have a lower bound. And we are going to demonstrate this final step by contradiction. So by way of contradiction, we will suppose the opposite. We will suppose that positive values of a plus b root 2 actually can't get smaller than some positive value a naught plus b naught root 2. And we will show that this is wrong, therefore proving what we want to prove. And to get started with this argument, we observe that there must be a number a plus b root 2 between consecutive multiples of a naught plus b naught root 2. And here k is just some integer constant. So first of all, we will simplify this inequality a bit. We will subtract a naught plus b naught root 2k from both sides. So we get that 0 is less than or equal to a plus b root 2 minus k times a naught plus b naught root 2, which in turn is less than a naught plus b naught root 2. So we have this inequality right here. But because a naught plus b naught root 2 is what we assumed for the sake of contradiction to be the smallest positive number that can be represented in this way, and since this number right here, which of course is of the form like c plus d root 2 for some constants c and d, because this number is less than the smallest positive number which can be represented in this way and greater than or equal to 0, it must be equal to 0. So this right here equals 0, and we get that a plus b root 2 for all a plus b root 2 must be equal to k times a naught plus b naught root 2 for some constant k. So every single number that can be represented in this way must be a multiple of the smallest positive element. But now an interesting thing happens. If we rearrange this to isolate the root 2, we get this equation right here. So root 2 equals a minus ka naught over kb naught minus b. But a naught, b naught, b, and k are all integers. Therefore, this side right here is a rational number, right? This is rational. Root 2 is irrational. Therefore, this is a contradiction. Therefore, a plus b root 2 must be able to represent numbers as close to 0 as we want, and therefore it can represent any real number. So f prime of y has every real period, and therefore it is a constant. Therefore, f of y is linear, which we wanted to prove. So this is a pretty neat argument. I think the really interesting thing about this is that it all hinged on the fact that root 2 was irrational. For example, if the two periods were 1 and 2, right? Like, for example, we wanted numbers of the form a plus 2b, then this argument wouldn't work. There would, in fact, be a smallest possible positive number that can be realized this way. In the case of 1 and 2, this number would be 1. Therefore, f prime of y would not be periodic with every single real period, and f of y would not be a linear function. So actually, if these periods are, in general, t1 and t2, this entire argument hinges on the fact that t2 over t1 are irrational. So this is actually a well-known neat result in group theory, right? When I actually got to this stage on the MIT Primes problem set, I just referenced this fact. But I do think that it is helpful to see sort of how this argument works, and I will post a link to the description for a generalized proof of this famous fact right here. So hopefully you like this video. Thank you for watching, and I will see you next time.